OK, so to wrap up what we've talked about for block ciphers, this is what is actually used in real life. It's something called AES, and it uses the underlying Reindel algorithm. It could have used Twofish if they liked David Wagner's design more, but they used AES. There are different key sizes you can use. So there's actually different pieces of code depending on the size of the key. There's AES 128, AES 192, and AES 256. And each one works roughly the same in that once you pick a key, it gives you a mapping, but the input key size is different. Nowadays, most people use 256 because it's the largest and hardest to brute force. But even if you used 128, it would be absurdly hard to brute force. The block size is usually 128 bits all of the time. So what that means is that n is 128. Once you pick a specific key, you get a mapping of all 128-bit inputs to all 128-bit outputs. And there are 2 to the 128 arrows dropped in that diagram. Now, we don't really draw the diagram. We use code to come up with which arrows point where. But that's the idea. It's a mapping of 2 to the 128 inputs to 2 to the 128 outputs. And you don't need to know what's going on inside AES besides that it's doing a bunch of bit shuffling. But you do need to know what the inputs are and that these are usually the commonly accepted sizes. And this is actually what people use in real life, too. If you really want to know what's going on inside, we have some extra slides here that I'm not going to say out loud. But what you can already see is that it's doing a lot of bit shifting, things that computers like to do, like subtracting, shifting, mixing the columns around, moving data around, swapping bytes. So it's doing all this shuffling, but the ultimate behavior is like we presented. It's a permutation, where every input corresponds to exactly one output, but which output is unknown to the attacker. It looks like a bunch of random arrows were dropped in. Here's more shifting. Here's more mixing. So it does a lot of mixing around to scramble up the input so that the attacker doesn't know what was presented. OK, here's more shifting. It's a long algorithm. So don't need to know what the algorithm is, just that it does a lot of shifting. And it turns out, has anyone actually proven that AES behaves like a random permutation? Has anyone actually gone and proven that Eve could not tell which box was which? The answer is actually no. Nobody has actually proven that Eve is unable to tell the two boxes apart. There maybe is some attack where Eve is able to tell that one of these boxes came from AES, because maybe they examined the code really carefully and they realized that the code generates this set of arrows more commonly than this set of arrows. But as far as we know, it's been 20 years and nobody has broken it. So it's as good as secure. So even though there is no proof, basically everyone uses it. Banks use it. The US government uses it. You use it. So this is the modern standard for what everyone uses as a block cipher algorithm. So before we totally leave block ciphers altogether, let's talk about why we don't stop here and declare victory and say that we're done designing a cryptographic scheme. The reason why we don't stop here is because of some problems that we've already seen. One problem that is very big is that block ciphers are not in CPA secure. They do behave like random, which means that attackers don't know where the arrows are. But because you use the same key to encrypt messages many times, they are not in CPA secure. They are deterministic for the attack that we just saw before, where you ask me to encrypt the same thing twice, and I get the same output. So intuitively, it's not secure because you as an attacker can detect when someone is sending a message twice. If Alice sends a lot of messages, and you notice 2 of the ciphertexts are the same, you now have a clue that Alice sent whatever that thing was twice. You learned information that you were not supposed to know. And the in-CPA game reflects that model that you don't want that to happen by forcing Alice to lose in scenarios where the scheme is deterministic. So the game reflects the reality. We don't want people learning if things are encrypted twice. So block ciphers are not in CPA secure. We need to go finding something better that is IND CPA secure. And the second problem that we've sort of hinted at, but we haven't really solved, is that the input and output are fixed size. So in fact, AES in real life can only encrypt 128-bit messages. If your message is shorter, you cannot pass it into the algorithm. It doesn't understand your input. And if your input is too long, you can't pass it into the algorithm. It doesn't understand your input. All of that bit shifting and mixing that you saw, it just doesn't work if the input is not 128 bits exactly. So if you want to encrypt things that are longer or shorter, you can't use block ciphers. So there are two big problems. One is security, one is usability. And to solve them, we're actually going to use block ciphers as a building block to build something even better that will be NCPA secure and will solve these problems. So that's coming up next.